dumb charge separated and everything. So we're gonna do, let's just do that step. I don't know. Okay, then we can do this step. Stop hitting each other. Cut it out. And that goes here, and this goes here, right? And then, I mean, I guess if we really want to get picky about it, we could do that, and just be really annoying about it. There we go. I think that covers them all. Because you can't make this guy negative. Yeah. Oh, wait. There we go. Oh, no, and then I guess I missed one because we can have, if that's all the way charge separated, then we can do that. Yeah. But I mean, these guys, these are really what we're looking for, right? Or, yeah. Or especially this one and this one, because we can just take these want to go up, these can go that way, and we get this, right? So yes, we end up with a carbon that doesn't have a full octet, but that negative goes up here, so this negative goes with that. If we do charge separated, but like, oh, yeah, it's charge separated. I mean, it has a better looking one. But this kind of can show us that on this, we've got some partial negative going on here, right? We've got some partial negative going on here. Not near as much as on the oxygen, but like some. It exists. Because we can, if we get really annoying about it, we can get some resonance structures that have a negative charge there. So we've got a positive or a partial positive charge here. Well, we know that. That guy always acts as an electrophile, like all the time. But we can also get a positive charge out here. This is why we're able to all of a sudden take an alkene, a double bond, carbon-carbon double bond, and call it an electrophile instead of a nucleophile. Because it's not that just this double bond is an electrophile, it's that this whole conjugated system here kind of makes room for everything to move out of the way, and that guy ends up with a partial positive charge. So, if we start trying to add nucleophiles to this, well, there's two things that can happen, right? Because we just figured out it could add there, but we've known all along it can add here too. Like, we're still not ruling this out. This is totally still there and totally still a partial positive. That's totally still an electrophile, right? So, okay, and these are examples of microreactions. I'm going to talk about what happens, and you'll see what happens. So microreactions with enolate anions give products with oxygens in a 1-5 relationship. 1-5 being, let's see. and 5 being 1, 2, 3, 4, 5. I think we count carbons 1, 2, 3, 4, 5. And we're counting starting at the carbon that has an oxygen on it and ending with the other carbon that has an oxygen on it, not including the actual oxygens as part of it. Which I guess makes sense for most things. When we get to stuff that starts looking like this, sometimes I start counting the oxygens because if we're doing a ring, I just want all the ring members. Okay, so. The adjacent carbonyl group activates the carbon-carbon double bond for a nucleophilic attack, and we can get this funny-looking thing. Let's just erase this. So what we end up with is we have our, God, I just don't like pointing at things, I like drawing them. All right, so we deprotonated here, so we've got that alone pair and a negative charge. This is our donor carbon, our nucleophile. And yes, there's resonance, but whatever. Then we've got, usually, this guy, right? And this is our electrophilic carbon. But now we've got this guy, and both of these look like electrophilic carbons. So what do we get? There's two possible products, right? One of them happens when this guy attacks like we're used to, and we get that, this green, it has, and I'm not going to worry about acids or bases happening right now. Get it on to the red guy, and the red guy has an, oh, here, I've got a better idea. That's now that. This is the red guy. Yeah, that looks much better, way easier. Now we've got this. But the other thing we can do is we can do red. We can attack here, which pushes these here and pushes these here. Then we get that was our nucleophile. This is our new bond. That was our electrophile. Double bond coming off of that. There we go. Now, we can do things from here, right? I mean, over here, we're going to start trying to look for a leaving group, or we're just going to protonate that and call it an alcohol. Over here, well, we've got an enol. So, yes.
Is that double bond not supposed to be right up on the the carbonyl carbon?
Yep. Thank you. Good call. That whole point was to make the carbonyl carbon happy. All right, there we go. Yeah, and if I had drawn hydrogens, I would have seen that. So draw your hydrogens while you do things. All right, so this one, there we go. Now this looks like an enol, right? And instead of just protonating that and turning it into an alcohol, we can tautomerize this and we can get back our CO double bond. So, both of those can happen. Okay, what do we do with this information? How do we know what happens in what situation? Or why are we even talking about one or the other if only one of them happens? So, see, combinations of reagents for effective microreactions. A lot of the time, we're going to have, most of the time they have these nice beta, whatever we're going to call it, diketone, ketoester, ketonitrile, diester, whatever it is, they're two carbonyls beta to each other, right? Whatever's stuck on the other end of it, it's two carbonyls beta to each other, which means that carbon in the middle, or in this case, a carbonyl beta to a nitrile, which is still gives you that extra acidic hydrogens on that middle carbon, right? More so than the ones on the side, because these, we only have one option, one carbon option that's alpha right here, and it's got hydrogens. Up here, this is also alpha to a carbonyl, and so is this, but this is alpha to two of them, right? So this is where we're going to deprotonate, like the most acidic. So usually we do stuff like that, where it's very obvious where we're going to have something, where we're going to have the deprotonation happen. And then we can do unsaturated, alpha-beta unsaturated carbonyls or compounds. We can do aldehydes, ketones, esters, amides, but you can also do nitriles and nitro compounds. So nitriles, C triple bonded to N, we just sort of see that as, like a nitro compound looks kind of like a carbonyl, right? Nitro kind of looks like a carbonyl, not entirely, but like these guys are alpha to it, so if we have, we're looking at alpha, beta, if we've got a double bond there, we can still do loop, loop, and get, that is resonance. That still has a plus charge, but now so does that. Now we can have resonance arrows. And if we've got a nitrile, we've got CH2, CH, C, N. We've got a triple bond, right? Only one of these is useful in terms of resonance with this, correct? Because what shape do our p orbitals make? Or what shape does a triple bond make? We've got the direct overlap in the middle, right, of the sigma bond. And then we've got the up and over of the p orbital with the like side overlap. But then where's the other one? Here, right? So this guy is going this way. This guy is going like this. And then right next to him, the guy's going like this. And they can really easily do this, right? And do some resonance. But the electrons that are here, they just stay here. They're not getting to hang out in this like above and below the molecule space. So they're not doing resonance with the other things, right? Are we good on, okay. Geometry. So, we can do that. That already had one of these. And now we get that and double bond with some electron withdrawing things next to it, like any of these guys, we can do a Michael addition. So, okay, I can draw out. This has me trying to draw out all of the carbons for you. I don't know. Look at that. Kind of like what we had drawn. We should have kept that. Yeah. All right, we'll start with. Oh, really? Really? This wants me to call this your nucleophile. I don't want to do that because I want like stuff attached to it. Is that cool? Okay. Because like sometimes using on groups is helpful because you can imagine more things on there, but just throwing an NU is just okay. What? Let's make. Let's not look too much like acetoacetic. Let's do this and that. So this is our nucleophile, right? It's where the hydrogens are real acidic. And let's make this guy look like this. We can just do that, right? Do we want to add some more stuff? You want to add more stuff? Okay, cool. All right, we have, this guy could be an electrophile, right? But we're already talking about Michael addition, so let's do the mechanism that's new to us. If we first do a step where we, oh, that's not what I wanted. There are too many colors. All right, let's take a base. We'll call it that. Yes, I'm very hypocritical in times that I'm okay with having the generic and the not, but whatever. We're going to do that, and we've got this. So we're going to deprotonate that, right? And we could put that up here if we want. Doesn't super matter. And we get this. Now, because I'm lazy, I'm not going to redraw that. We are going to take the electrons, and I keep wanting to draw right from the red, which is why I keep making this double bond also red, because we have to draw from where the electrons come from, right? Not just the carbon that ends up nucleophilic. So when this can come back down and reform its double bond, which frees these guys up to go attack right there. Yes? This guy goes, hey, I'll just hop over next door, no big deal. And this guy's like, I'm an oxygen. I love all of the electrons. I'll hold them for you. I'll totally give them back, maybe. And we get, okay. I'm going to draw this. We're going to do this. That works, right? These carbons need to be a whole different color, don't they? Yeah, we're going to color code. Okay. Now we've got a new bond to this guy. And this is 1, 2, 3, 4, 4 carbon chain. So 1, 2, 3, 4. 1, 2, 3, 4. All right, 3 is where that is. So that was going to be a double bond, but now it's just that because we have this next door. So we just move that between 2 and 3. Yes? We remade those, so those are fine. Now we have this, and let's see. Oh, we started this with a base, right? So this is in basic, a basic environment, basic situation. So let's not protonate that into an alcohol. We could, but then we're just gonna undo it because this is an enol, right? So instead of protonating that and then deprotonating it, let's just start here and do enol things. Because from here, make sure I'm doing what, okay, yeah, so I thought. From here, we have, remember we had just base B minus before? So now we've got that. We can take this guy and go, hey, I really like making those double bonds. So I'm gonna come back down and do that. I'm gonna draw this up here, even though my handwriting got bad because it's way easier to draw the things. These electrons can go, well, if you're gonna come down here, I have to get kicked off. So I'm gonna go protonate myself, and that's gonna go here, right? Because we just added to this guy. So, as we do sp2, 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 sp3, right? We added to this guy, that was addition. So now this guy is already sp3. These guys are sp2 because, well, they've got a double bond. And this guy, we could call it sp2, or we could call it, whatever. Yeah, that guy's sp2 because it's in conjugation here. So, when we bring that back down, we're fulfilling the double bond that these two sp2s want to have, right? So, this is the carbon that gets the hydrogen, right? This guy comes up and goes, hey, I would like some hydrogen, please. And we get we just reformed this, so this gets to stay sp2, this gets to stay sp2, this guy was sp3 all along, this guy became sp3 when we attacked it in the first place, and these electrons that started here went and got a proton, so even though this guy has one proton right now, over here, it got itself a second proton, and it's sp3. Yes? Does that make sense? All right. Same exact thing, but we attack the wrong guy. This is pre-deprotonated for us, because I feel like it. Yeah, so there's just one hydrogen there. And let's take this guy. All right, so if we were to just do what we're used to, an attack here, then this is our memory file. And we would attack there and push that up, and we would get new bond. That carbon, and this is 1, 2, 3, 4, I guess we can call it, or this is not the when I number stuff like this is not the way we number stuff for naming. I just don't test you on that anymore because I don't know, I don't like it enough. There we go. That's probably more correct. Because I think this takes precedence. Anyway, however we're gonna do it. If we do it from here, this means this guy is 2, so he's connected to 1 and 3, 4, and also that, right? Now, what can we do from here? If we want to reform this double bond, is there a leaving group? Not really, right? I mean, I guess since this is acidic, we could call that a semi-okay leaving group, but like, oh, duh, that's just this reversible reaction reversing, right? So the only way to go forward with this is to get, gosh, I'll stop in a second. Too many colors. Is if we grab the BH that we had from earlier, we go, hey, let me just go ahead and protonate. And we end up like this, right? So, which one's more stable? New way or old way? There's a lot to look at, but what's the one thing we care about? Reforming. CO double bond, right? Because CO double bond, more stable than 2 CO single bonds. More stable than a CC double bond. More stable than like a bunch of other stuff. So this guy's gonna be favored, right? If we've got a bunch of reversible reactions, which so far every step that I've written up here is reversible. I guess this has to come from, yeah. Every step up here is reversible, right? So if we're just going to let this reach equilibrium, thermodynamic equilibrium, we're gonna have this, right? What's the way we would try to get this kind of product if we just call this a nucleophile, a generic nucleophile? If we're gonna try to, is there a way that we can use a specific nucleophile or a specific type of nucleophile to attack here rather than here, and for Michael addition? Well, we can get this product if none of this is reversible, right? If this first attack right here is not reversible, like say if we have that, yeah, all of a sudden, yes, this is going to attack some here and some here, but if we attack here, we're gonna stay there, right? So then it becomes which one is this actually going to do? This carbon's more electrophilic, right? This carbon is way over here, and there's some pulling in the pi system. So this guy has a partial positive. This guy has extra partial positive because the pi system is pulling electrons away, but also its sigma bond is polar, right? So this guy's more positive. This guy wants to be attacked first. So this guy, if we have no reversibility, then we can be under what we call kinetic control. So kinetics are in control. Whatever happens fast stays that way because we're not reversible, and this guy's not reversible, and that's what happens fast. So that would give us oh, 1, 2, 3, and this stays there. And we can protonate that later, right? This is the product we're going to favor in this case because this guy's gonna wanna get attacked first. It's more electropositive. And once we attack with this guy, can't go backwards, so we can't hit equilibrium. So thermodynamics don't matter, right? It doesn't matter what product is lower in energy, it matters what we get to first because we can't undo anything. Whereas up here, everything is reversible, everything's undoable. So even though this reaction would happen first, right? First, we're gonna attack the guy that's more electropositive. It's just, we're also gonna undo that reaction just as quickly. And if we let everything settle down, eventually we'll live here. Thermodynamic equilibrium. So